energized optimization sludge treatment. A little introduction about the plant itself. We are more or less in the industrial district in Vienna. Over the street, on the other side of the street, there's the incineration plant for hazardous waste and sewage sludge. So we pump there our sludge to get incinerated there. There is the MVE Pfaffenau, that's just domestic waste incineration, and the harbor is next to us, and you can see in the picture our area or wastewater treatment plant. A little overview about my presentation today. Just some words about the history, because we grow, of course, so over the years we get bigger and bigger. Some facts about our wastewater treatment plant here in Vienna. Then what we did for increasing our energy efficiency 2005, and our main focus on the project EOS. So we'll start with the history as mentioned. You can see just a picture of our wastewater treatment plant there. In 1980, we start to build the only or biggest wastewater treatment plant here in Vienna. We are the only wastewater treatment plant here. In 1980, we start to build our first stage. You can't see it here on the picture because you will see it later on. We operate there as the main wastewater treatment plant in Vienna, and we removed there only or mainly carbon. In the year 2000 to 2005, we start expanding our treatment plant. You can see it in the picture on the southern side or upper side on the downside of the picture, the 15 lines, 15 final clarifiers. We built that in 2000 to 2005. We expanded the plant because of the needs of removal of nitrogen and phosphorus there. That was the main reason why we built that. And then, of course, that removal costs a lot of energy, and then we thought we have to do something else. We have a lot of sludge there, how we can think about it, how we can reinvent our plant. That happened between 2015 and 2020 with the project EOS. Some facts about our wastewater treatment plant. We are the biggest wastewater treatment plant here in Austria in terms of area, capacity, and influent. We have 490,000 square meters, so that's bigger as the Vatican City, if you need an expression how big that is. We do have 2 million cubic meters, 200 million cubic meters influent per year, so that's 500,000 cubic meters every day, and in average 6 cubic meters per second. So we have a lot of influent here. Our capacity, we do have in Vienna around about 2 million residents here. Our load is around about 3 million population equivalent here because of industry and tourism, of course. And our plant is designed to 4 million population equivalents. We are a two-staged wastewater treatment plant. So the first stage, high load carbon removal, and the second stage is for nitrogen and phosphorus removal, as mentioned before, with an anaerobic sludge stabilization. We are one of the biggest even in Europe. So we are, I think, the 5th biggest wastewater treatment plant in the European Union. And our energy demand around about 64 gigawatt hours per year. So that's a lot. What we did before the project EOS, we started to rethink everything here on the plant. We started to get our renewable energy sources going, where we can get some energy. Let's start with the project SternE or STARS. It's energy out of renewable sources. We built a wind power plant. We built a normal solar power plant, a smaller one, of course, there. And we installed a hydrodynamic screw and a Kaplan turbine because of high difference to our river where we put the effluent. So we tried to use every opportunity here on the plant to get energy out of the waterway, and we can use heights and every place here on the plant to get, or every spare place and area on the plant to get out energy for that high energy demand we had. With that, steps, we can reduce our electricity demand by 11% roundabout with those smaller projects, or the project SternE in 2005. Without Project EOS, we had 3% of the required electrical energy was generated by renewable energy sources until 2019. Until then, we used or required 1% of the Vienna's electricity consumption. We heard it before at Asho's introduction about wastewater sector and the energy demand there. Okay, now I would suggest to focus on Project EOS, because that was the milestone here in Vienna to get really big in energy operating that project and getting renewable energy here in Vienna. And why we did that? It was not only the energy. The first biological treatment step was built in 1980, so it was almost 40 years old by 2020. And what we have to do is to get a new one. We try to should we get everything repaired, and so we took that opportunity and made an optimization of the overall system here in Vienna. Newer tanks, newer technologies, newer pumps, and so on and so on. We re-evaluated the sewage sludge as a residual product. Before the Project EOS, we just pumped the sludge to the incineration plant on the other side of the street, and it gets incinerated there. The new approach was we can use it as energy source and be self-sufficient here, and then the leftovers will get to the incineration. The goal was the energy positive operation through the utilization of energy in the sewage sludge and increasing energy efficiency by all the new constructed plant components. That was the main goal in Project EOS. What were our innovative aspects? In Vienna, we have a two-stage process technology. We wanted to minimize the energy for aeration, so we have the first step for higher sludge production, here in red, maximizing the sludge production. That was a goal in Project EOS. And for the gestures, of course, and the gas production afterwards. So what does this mean? We built our sludge digesters. There was an innovative aspect. We would have need 12 of the big sludge digesters, but we go with minimizing the water content, or putting the dry solid content up. So we used around 6 to 8% dry matter in the sludge. That's more than usual. And what we can get there is the minimizing heat requirement for the digesters, and also the volume is half that big because of the higher dry solids in the sewer sludge. What was our goal there? Maximizing biogas projection in the new digestion, of course. And then we have a very highly efficient combined heating and power plant here on the wastewater treatment plant, 5 of those, to produce electrical and, of course, heat energy. What was the scope on Project EOS? The construction and planning phase 2015 to 2020. We had to operate the whole plant all the time, so that was a real challenge here in Vienna to get everything going, and also renew the first treatment step and build the sludge treatment as well in the time from 2015 to 2020. What we did is reinvention or the reinvestion in the water line. We built a new primary sedimentation with 28,000 cubic meters. We built a new blower station and a new biological treatment step. 1 is it called in Vienna, with 50,000 cubic meters. We also needed a new intermediate pumping station, and also a new intermediate sedimentation to get all that sludge collected and in the thickeners there. What did we build new in that time? We built, or we needed new mechanical sludge thickeners here, 5 centrifuges to get the dry matter up from 4 to 8% approximately. We built new 6 digesters with a total volume of 75,000 cubic meters. We have a digested sludge buffer tank that's for incineration reasons, because to pump the sludge to the other side and they get a storage. And 2 gas tanks with 5,000 cubic meters in total volume. And also 5 combined heat and power plants with 3 megawatt electrical and 2.7 megawatt thermal power, and a hot water boiler with around about 12 megawatt thermal power in case of needs. And a separate reject water treatment, though we get all the reject water back from the sludge incineration plant over the street, and we pump it here in a separate reject water treatment to get even more energy and aerate efficient here. Essential compounds, once again, some pictures of our plant: 6 digesters, 75,000 cubic meters, 2 gas tanks with 10,000 cubic meters in volume, and those before mentioned 5 combined heat and power plants. And I would say some results that shows what we did and what we achieved here in Vienna with the project EOS mainly. In 2019, you can see the stats here from 2019. That was the last year of operating without EOS, and 2024, that was as an example year of operating with EOS. The first graph shows us the electrical energy consumption, generation, and the external demand or the delivery we did have from electrical energy. So in 2019, we used 59.4 gigawatt hours per year. In 2024, it was 65.4 gigawatt hours per year, because of all the new plant parts, and the sludge treatment needs power as well, electrical energy as well. So that's why the demand goes up a little bit here. We generated in 2019 1.5 gigawatt hours. In 2024, we produced 73.9 gigawatt hours on electricity here on the plant. We needed 57.8 gigawatt hours in 2019 from the external grid. In 2024, we used 1.4 gigawatt hours, so just for electricity demand spikes because of flood water or rainy weathers. Then we need a little bit of external energy from the grid. What we did delivered on electricity energy in 2019, 0, of course. And in 2024, all the overflowing electricity energy was delivered to the grid, to the Viennese power grid, and that was around about 9.8 gigawatt hours in 2024. Thermal energy, the same graph, the same stats from 2019 to 2024. You can see there we needed 1.9 gigawatt hours on heat in 2019. 2024, of course, for heating all that sewer sludge to 38 degrees, we need a lot of thermal energy to get the temperature up. In 2019, we don't have any generation on site of thermal energy, just a little solar heat collectors on the plant. And 2024, we have 64 gigawatt hours on heat generation here on the site. We need 1.9 gigawatt hours in 2019, and now we need 0, because we have a lot of overflowing thermal energy here. And all the overflowing energy we put in the power grid of Vienna for the households there. What is the degree of self-sufficiency here on the plant now, then and now? In 2019, we have 3% self-sufficiency of electricity energy. Now we have 100, or in 2024, we have 113% self-sufficiency. I can say in 2025 we had 111%. In 2019, thermal self-sufficiency was also 3%, and now we have 170% self-sufficiency here in Vienna. So we have achieved with the project EOS that our whole energy demand can be produced by ourselves and even more, and the overflowing energy we can put in the grids of the city and support the city with power and heat here. Okay, I'm at the end of my presentation. I think you have a good overview what we did here in Vienna with smart construction, smart planning, and all the work behind the project EOS mainly. Thank you very much.
Thank you very much, Sasha. That was a very insightful presentation and sharing a lot of experience from the Vienna on energy generation and energy recovery. I see some hands now, but we have 2 more presentations and we are planning to have a Q&A session at the end of all the presentation, but you are also welcome to post your questions in the chat now as well. Now, I would like to move ahead with the next presentation, which focus on the role of digitalization and artificial intelligence in improving energy efficiency of treatment plants. I would like to introduce Ms. Pauline Lauren, Chief Marketing Officer at Pure Control. She has been with Pure Control for past 3 years in supporting the company's work on AI-driven solutions to reduce energy consumption and optimize industrial and water networks. Pauline, the floor is yours.
Okay. Good afternoon, everybody. I will share also my screen if I can find my presentation. Yes, here it is. So, the topic of today, I would like to tell you a little bit about Pure Control technology and how artificial intelligence can improve energy efficiency of wastewater treatment plant. And I will take the example of Rennes Métropole, a French city, and this is where also Pure Control company is located. First, as an introduction, I want to underline the fact that energy efficiency is a highly multidimensional strategy. And at Pure Control, what we are doing is to work not only on consuming less, but also how can we consume better and also manage flexibility. And this is where artificial intelligence has a great role to play, because using AI at Pure Control, we managed to combine various levels of optimization towards energy efficiency. Meaning, we will be working on improved efficiency without the need of replacing equipment, simply by using real-time analysis of data to identify what would be the best set point for equipment, for pump or air blowers, and to reach a better yield. We will also work on advanced calculation to identify what it is the strict requirements in terms of running time to reduce running time and avoid overconsumption over quality. Using AI also allows us to take into consideration the presence of renewable energy on site to improve self-consumption. And we can also take into consideration the source and the cost of electricity, which highly matter in the equation. So we will take into consideration electricity tariff variation, but also carbon intensity. And on a more holistic point of view, we can implement multi-site power modulation upwards and downwards, because wastewater treatment plants as a whole have a great role to play, helping to balance the national power grid. As we know that in France and in Europe in general, national grid comes with more and more renewable energies, which are highly intermittent. And this is a great challenge to handle with. I will today focus on wastewater treatment puzzle, how to reach energy efficiency while also reaching operational regulation and environmental challenges. I will also have a great focus on aeration, because we know that in a wastewater treatment plant, aeration is responsible for 60 to 65% of the total electricity bill of a plant. And at an operator scale, working on energy efficiency while complying with a new regulation and while taking into account carbon footprint and nitrous oxide emission, for example, is highly complicated. And this is where artificial intelligence and advanced technology can help. How do we do so at Pure Control? We blend extensive data sets and we'll focus on analyzing plants data itself, so sensors, on and off status of air blowers, speed variation, and so on. And we will cross-reference this information with external data such as electricity tariff variation, weather forecast, carbon footprint, and so on. And then we will ask what are the operator's constraints and objectives. And with all those data sets, we can create a digital twin that we will use to simulate optimum scenarios. And what is more important at the end, that when we have identified an optimum scenarios, we will directly transmit this information and translate it into instruction to the PLC in order to remotely activate air blowers, pumps, and so on, any piece of equipment we want to optimize. We will send instruction to control equipment remotely in real time and updating those instructions every minute. Today, I want to share with you an example of the project we carried out with the city of Rennes for a few years now. And Rennes has decided to use Pure Control to improve energy efficiency, of course, but also to improve its carbon footprint. Just to give you an overview of Rennes Metropole Sanitation Department, the wastewater treatment department handles 25 plants and is serving around 200,000 households here in Rennes and around. For a few years now, as I said, we've been working on aeration optimization, but also phosphorus removal, improving self-consumption of renewables, and reducing greenhouse gas. Let's talk about aeration process and the key results we managed to achieve in Rennes. Working on aeration process with our technology, we managed to reduce energy cost by 15%, while reducing the associated carbon footprint by 25%. And those results always come along with ensuring compliance, of course, and having an early detection of anomalies. How do we do so? How do we manage to obtain those results? Here, what you have on this chart is a planning of activation of air blowers, aeration cycles planning. In the middle of the chart, it's T time. On the left, you have aeration cycles on the past and in real time. And on the Y side, you have a plus 24-hour prediction carried out by our AR algorithm. And what we do at Pure Control is that we will create a planning and update this planning every minute using a prediction we make regarding the physical chemical parameters within the plant. We create what we call a virtual probe of ammonia to anticipate how the load will evolve in the following hours. Accordingly, we will calculate what is the strict and required time of functioning for air blowers, and also taking into account what you can see on the yellow curve, electricity tariffs. Okay, so you have peak and off-peak hours, and what we want to reach is to reduce running time, but also activate air blowers when electricity is the cheapest, or it could be when electricity is with lower carbon intensity, for example. So, how do we calculate those results? Simply, in this example, so this is the biggest wastewater treatment plant of Rennes. It's 260,000 people equivalent. Okay, so on the left you have functioning of air blowers and running time before Pure Control was activated. And on the right side, when you see the blue halo, it's when Pure Control is running on the plant. So we are comparing performance in terms of discharge, because this is priority number one when you talk about a wastewater treatment plant, of course. And we are also comparing daily aeration time. And this is how we can calculate that we are able to reduce aeration time by 15%. We look at running time, we look at aeration consumption, always by comparing what happens when Pure Control is activated or when Pure Control is deactivated. So you see that regarding air blowers, we managed to reduce aeration consumption by 19%. Another example and another constraint we can take into account. So here it's a different wastewater treatment plant here in Rennes, equipped with solar panels. In this particular situation, we will not only take into consideration quality and compliance, electricity cost, but also the fact that solar panels on site will produce energy, and then we will try to activate blowers, the most energy consuming equipment, when solar panels are producing this energy. And using AI, we managed to improve the self-consumption by 18%, while always acting on reducing energy consumption by 15%. As a conclusion, I just want to raise your mind about one specific point, because it's often said that artificial intelligence consumes a lot of energy and a lot of water resources. And it would be contradictory to use artificial intelligence in the world of water if it was strictly the case. First thing I want to say is that when you talk about artificial intelligence, there is a lot of different technologies inside it. In the case of Pure Control, we are not working and we are not developing generative artificial intelligence using LLM. We have a specific technology that we have developed on our own using machine learning and model predictive control. And the difference at the end is that when you compare our own energy consumption to the savings generated by Pure Control, the benefit is very high, because our consumption only accounts for 1% of the saving generating. This calculation doesn't come from Pure Control itself, but it was carried out by a study of the Collège de France, with the head of Philippe Aghion, which is a Nobel Prize of Economics in 2025. So yes, just as a conclusion, a few words about how to differentiate this kind of technology and to better assess its relevancy in terms of energy consumption and water resource saving. Well, thank you so much for your attention. And I leave the floor to the next speaker.
Thank you so much, Pauline. That was a very interesting demonstration of how potential AI and digital technologies can support more efficient wastewater treatment. Thank you, and it's time for us to move to the next presentation, and it is my pleasure to introduce Mr. Koos Wessels, CEO of SternE BV. Koos has more than 30 years of experience in innovative water purification and resource recovery technologies. Under his leadership, SternE has developed advanced solutions for recovering valuable materials, including cellulose from wastewater streams, supporting more circular and sustainable wastewater system. Koos, the floor is yours.
Yes, thank you, Ashra, for your kind introduction, and thank you for giving the opportunity here to present something about our reference project. Let me see now where I can find the right screen. Let's do it this way. Oh, what's going on now? Again. Now you see yourself, I think. This should work, isn't it?
Yes.
Yeah. Okay. Yeah, in the title, I refer on the agenda to the Smart Plan project, what is a Horizon 2020 development project where we first tested our technology on a larger scale and where recovered material was all utilized as a renewable raw material. So I'm trying to jump directly into technology. Certec is since 2023 part of Solar
Ouais, je
Industries.
t'entends, mais je suis sur à écouter un...
It's since 2023 part of Solar Industries, and yeah, that's as far as I want to jump into our company. We go directly into technology. I would say the road to net zero carbon. Water utilities, they have some significant challenges, as Ms. Malarga also highlighted in her introduction. They are not only expected to treat or purify wastewater, but they have to become energy neutral. They have to live up with the circular economy principles, and at the same time they have to stay economically responsible with our money. And this was also for us a part of start of our technology development. What we do is we take cellulose from sewage. And how do we do it? Just behind the core screening, we install a double-stage filtration technology, harvesting a highly organic fraction from sewage that can be digested and can be turned into biogas, what fits in the energy neutral principles. And next to that, we harvest a clean, marketable cellulose that has only limited biogas potential. And what does it do? It relieves the activated sludge or biology from a certain load, so reducing energy, reducing sludge volumes, meaning that you save on dewatering, on polymer, and on additional chemicals. Some numbers from our project with regards to savings. We will share these slides, so I will skip a few of them. But basically what you do on a typical wastewater treatment plant, we would reduce COD to a level of about 30% and 50 to 60% of the solids. It's only a limited amount of nitrogen that we remove and a limited amount of phosphorus. So we have to look at BODN ratios to maintain denitrification processes. There are different technologies for harvesting material that also refer to cellulose recovery. But there is a huge difference. The majority is single stage screening technologies where you harvest a material that also contains fats, seeds, synthetic hairs, synthetic fibers, hairs, and everything. Or what we do with our two-stage machinery is we take out first the organics and then a clean cellulose. So the picture shows the difference. And it's important because if you want to reuse recovered material, it should fit in with an end of waste certification of approval that you get, meaning that you have to get rid of, I would say, the most variable materials that you can find in sewage. So from a perspective on how does it look, you see now an operating intensive from us, and you see an operating cell wash taking out the residual stream. And don't be disturbed by the color. The color is typically black, what has to do with retention time on a sewage system. But as soon as it dries, it gets its white color. First stage is organic material. What is important, you see in a lot of countries, biogas is an issue. So we looked at basically all sides about what is the biogas potential that we can recover from the material that we harvest from it. And we made an overview of that. So looking at dry solid materials that we harvest that are in between 8 till 11% of dry solids typically can be mixed normally with settled sludge to be fed into digester. But you can say that approximately 1 ton of residuals at 11% would have a biogas potential of about 65 to 68 cubic meters of methane. So not biogas, referring really to methane. In the meantime, we have built a couple of plants to do this on a larger scale, and this is a project we're working on. It's a treatment plant of close to 700,000 people equivalent. You see here 9 PSTs, and these PSTs are to be replaced by cellulose recovery technology. So you see it here on scale drawn. This is an installation to 2/3 of the part. So the part that is enlarged here, this part can replace 6 of these PSTs. So it gives you an enormous impact on footprint. Not only that, in case of you have stormwater issues, you can also free space for stormwater collection. The rest of what you see is post-treatment of the cellulose fibers that we have harvested. But I will come to that shortly. In quick, what does it mean if you harvest cellulose? You see that you save some energy on aeration. You remove basically hairs, fibers, and anything that will cause problems downstream in pumps and other equipment. You reduce the sludge volume. And on the same end, you don't see any differences on dewaterability or polymer consumption per ton of solids. So in general, you have less sludge. Doing 2-stage filtration, it means that you that you reduce something on biogas, but cellulose itself doesn't have a large biogas potential, so it's a limited reduction, and we see absolutely no impact on further performance. But then going a little bit into the circular objectives, once you have harvested this cellulose, sewage is a waste, so the material coming from sewage is also a waste. So we developed processes to use this cellulose as a fiber or as a carbon. And in this case, I highlight basically the use as a fiber. So the material that we harvest is dried and hygienized and then collected for further processing. Depending on specifications of the buyers, we upgrade or we refine this material and use it as a renewable resource in different kinds of materials. Our buyers, for example, they use it for making shoring and timbering. At the moment, we are building 15 kilometers of timbering for a water utility. We've done gladdings for a water utility using their own cellulose to cover their buildings. To give you an idea, in these kinds of biocomposites, somewhat like 65% of the material is recovered cellulose. So it's a lot, and the rest is recycled plastic. We also use it as an additive in asphalt or in other materials. Of course, if looking from a point of sustainability, you have to look at what is the impact of using these renewable materials, and also looking a little bit on costs of material. So there's the environmental cost index, and if you look at what it does for a bio-based fence, for example, and we took one or a barrier that's 2.5 meters, we would compare it with aluminium. You see that the environmental cost index for the bio-based material is about 98% lower than, for example, for aluminium barriers. Yeah, and if you look from CO2 footprint perspective, you see that it's over, I would say, 94%. What we do is at almost at the highest point of the sustainability ladder. So if we take over the whole value chain over the whole value chain, the impact on CO2, then depending on the application of the material, you see that we save 2 to 2.5 tons of CO2 equivalents per ton of cellulose that we recovered. It's a study that's done by Kompetenzwasser Berlin, taking a base sewage treatment plant, having core screening, having biological treatment, having a clarifier. Sludge is gravity thickened and returned into the biology, centrifuge with polymer transport, and then sludge drying and co-incineration. And what we did is we put in there our harvesting and drying, hygienization and refining from it. You see that you have then an impact on the wastewater treatment plant. What is negative? Our part does have a CO2 footprint itself. It is a positive number, but nevertheless, the total impact is negative. So even at the sewage treatment plant, there is a positive effect. And then, of course, you have a reduction on external processes, and you have an effect on the primary raw material. For one of the treatment plants that we have as a reference, there was an overall overview made by the total carbon footprint of a treatment plant. And this one currently has a footprint of 34,000 tons of CO2 equivalent a year. And with our installation, where we treat 2/3 of the capacity, we could reduce their CO2 footprint with approximately 20%. So it has quite an impact doing this at the sewage treatment plant. Of course, the carbon advantage is not all on the sewage treatment plant, but also partly outside of the fence. Then we looked at global warming potential. Actually, Kompetenzwasser Berlin did that for all the different parts where you have in the process, so electricity, drying, incineration, sludge, polymers, all these components. And then you see that basically the global warming potential, so the kilogram CO2 equivalent per people equivalent, would be somewhere in the area of approximately 3 kilograms of CO2 equivalents per people equivalent, less including our technology. We do that right now already at 3 different larger scale sewage treatment plants. So we do the refining ourselves, the sales, and we guarantee a water utility a value for the recovered material that we harvest and that we sell from them. Yeah, so in general, we're saving energy. We are harvesting a valuable material. We reduce CO2 emissions, and we contribute to both, I would say, the energy and circular objectives of a water utility. And the nice thing is we can do that with compact modular constructions. So for that, we also have a rental and pilot units that we can do. This could treat a small treatment plant flow for approximately, I would say, 20 to 25,000 PE on a skid-mounted unit. Something about cost, depending on the price of heat. So if we have access to residual energy that we can use for drying and hygienization, we see I would say a return on investment that is within 1 to 3 years payback time. If it's not, it can be something like 5 to 10 years. It's a little bit depending on the situation with regards to payback time, and of course the economy of scale. In first, we need to have some larger scale units to build also the marketing channel for selling the material and doing the end of waste process. So this is in a very quick scheme on what we do and what we have done so far. It's core business. We do that right now in 4 different countries. And in our philosophy, reuse of materials from sewage, it's not a choice, but it's something that we really have to do. So this is in short my presentation. Thank you for your attention, and Ashra, I give the floor back to you.
Thank you so much, Mr. Kos. So it was also a very interesting presentation, and it showed how we can recover resources from wastewater rather than it just being cleaning the water. So we are already a bit over the time, but still maybe if we can stay 5 or 10 minutes more, we can answer all the questions. I also see that there were some questions in the chat and which has already been answered. And if I check, there are also like one question. I think this one is for the first presentation from the question from Sachin. How is the biogas collected and approximate pressure and conditions of the gas generated? So, Sachin, if you would like to elaborate the question a bit.
Yeah. Hi, thanks, Arsha, for the opportunity. So my question is to Koos. When he was delivering the presentation on pure control, we see that a lot of biogas is generated. So just wanted to have an idea as to how, like, is there any contrivance provided which will allow for the capture of the biogas? And does it come with the technology itself, or is it like an additional installation that like an add-on of sorts? And what are the typical conditions of the gas that is generated, like at what pressure, so as to design parameters required for storage of the gas, so which can be deployed at the client or the installation site? So that some idea regarding that.
Yeah, thank you for the question. Actually, we talk about biogas potential. So in our installation or our technology, we do not generate biogas from it. But what we see in a lot of countries, you see that over the last couple of years, there have been a lot of investment done on digesters and biogas generation. So if we would start harvesting material, you should depreciate basically on what is already bought, and that would affect the economical feasibility of our technology. So we are not generating biogas, but we looked at the biogas potential by looking at normal digesters. Where we did do these pressure tests in bottles and see how much you can convert in over a timeline, and taking into account that an average retention time in a digester would be between 22 and 27 days on retention time as a minimum. This is how we calculated the biogas potential.
Fair enough.
If that answers your question. So
understood.
I see also the other question. It's with regards to how much fat and or sand get retained, and does the operator need a fat and sand trap after? This is a little bit. It's a mixed question that has two answers in it. We capture the majority of fats and we capture the majority of sand. So we use a kind of cake filtration. So we create a filter layer, and the sand comes into the cellulose fraction, where the fats come in the organic fraction. So you don't need any post-treatment like a FOG trap or a sand trap behind our equipment. Please take into account that it has some kind of limitation, so it's not a fat catcher or a fat trap. It takes out the majority of everything. The sand ends up into the cellulose, and after drying, due to the big difference between density of cellulose and sand, it's easy to separate it there, so it has no problem. And even when we use it for construction materials, it's not a problem after all, because typically they use sand in it as well.
Thank you so much, Koos, and thank you all the speakers. I would like to take, if there are any more questions, we can still spend 5 more minutes. But in the meantime, I would like to share. Okay, would like to ask you to provide your feedback of this event, and also to highlight that there are a lot more technologies that have been using for energy efficiency and resource recovery throughout EU member states, and some of these cases are being featured in the best practices catalog, which I already mentioned was released recently. And you are welcome to scan the QR code and look through the different methods available. Also, I would like to welcome you to scan the QR code and provide your feedback. If there are any other questions, we can answer it now. Or
I wrote a question on the chat to Mr. Kos as well. Just a follow-up question. What was the biggest system you installed or operated yet?
The biggest that we have in operation right now is treating 170,000 PE treatment plant, and it treats on an average flow somewhat like 3,800 cubic meters per hour. And the biggest one that's in design is 670,000 PE, where the design flow for our installation is close to 7,000 cubic meters per hour. And basically we don't treat the full flow, because when you have FFT, you see that water is diluted. So at a certain moment in time, it doesn't become feasible to start filtering it. So this is maybe why there could be a differences in PE size and volume. But
Yeah, thank you.
we also have one more question in the chat from Christian.
is this also to me? Did
No.
you look into? Oh, I thought so.
Christian? Yes, Christian.
Yeah. For me, it is a general question for the study. We've seen 3 excellent case studies, but did you also look into constructed wetlands as an energy efficient solution? You know, if it's like a benchmarking exercise, it's quite clear for a city like Vienna, constructed wetland would not be a feasible solution, but for smaller settlements, it might be an option. We have some industrial parks with 40,000 cubic meters a day, which also use nature-based solutions in Indonesia. So it would be interesting to see whether the study also looks into this in terms of energy efficiency.
So for the program under EU4Green Recovery East, we are also promoting nature-based solutions, especially since the wastewater treatment plants are located in or a place where for wastewater treatment plants located in villages, or where there are place or land available for this nature-based solution. But for the catalog that we have presented now, we have not included such a case study, since we are looking more into innovative and more new technologies. So this is a living document itself, and we are planning to add more cases. So in the future, we will also add more cases like that. But as you mentioned, construction wetland and nature-based solutions are getting a lot of attention in the present time, and it is also a very good solutions for the future. Okay, so I guess there are no other questions. So thank you all the participants. And as we approach towards the end of the session, I would like to invite Ms. Natalie Degger, Industrial Development Officer at UNIDO, to deliver the closing remarks.
Thank you so much, Arsha. We cannot solve our problems with the same thinking that we used to create them. I love that sentence, and I think that we are all applying this thinking as we look towards the facing the challenges of our current environment. So On behalf of UNIDO, thank you to all of our speakers and the participants for a really rich session and an engaging discussion, especially in the chat. I was monitoring and seeing the discussions going on. Today's session really reinforced a simple but important message. Wastewater treatment plants are no longer just facilities for managing waste. They are really becoming the engines of the circular economy, capable of recovering energy, water, nutrients, and other valuable resources while reducing costs, emissions, and environmental impacts. So the examples that we've seen here today have demonstrated that the technology and the solutions already exist. What I feel is really needed now is the continued investment, the innovation, and the collaboration to actually scale them further. Today's session also highlighted how the EU4Green Recovery East program is helping to translate these proven European experiences into practical action across the Eastern Partnership region. They're doing a fantastic job through knowledge sharing, their best practice dissemination, and the ongoing assessments in their pilots. And the program is also helping to identify concrete opportunities for implementation and investment. So, as the energy prices rise and resource constraints increase, improving efficiency and resilience of wastewater infrastructure is not only an environmental priority, but it's an economic necessity. From UNIDO, we remain committed to supporting our partner countries to advance circular economy solutions and sustainable resource management across the region. And I thank you once again for your participation, your expertise, and your commitment. We really look forward to continuing this important journey together towards a more circular, resilient, and sustainable future. So thank you very much.
Thank you so much, Natalie, and thank you everyone for your participation. I hope that this session provided you with some useful information, and I hope to get your feedback of the event, and we look forward to such more informative events in the future as well. Thank you all. Thank you, everyone. Bye.